Right now, beneath the pavement of one of the world's most famous cities, a massive physical system is panicking. When a heavy rainstorm hits London, millions of people continue their day completely unaware of the water vanishing into a network that has reached its mathematical limit. This is London's original combined sewer network. Built in the 1860s, these brick tunnels were designed to pull wastewater and rain away from a population of about 4 million people, a feat of engineering that functioned perfectly for a century. But today, London supports 9 million residents. The city's physical footprint has also changed. Massive areas of once absorbent earth have been paved over with asphalt. When rain falls now, it cannot soak into the ground. It sheets instantly into the drainage grates, hitting the system with immediate, massive volume. This urban density has transformed a Victorian triumph into a critical bottleneck. The pipes have a hard physical ceiling, and the city has finally outgrown the tunnels beneath it. On a dry day, the old pipes work fine, but with just 2 millimeters of rainfall, water volume spikes violently, hitting maximum pressure instantly. To prevent raw sewage from erupting from street drains, lateral overflows open, dumping excess flow directly into the River Thames. This happens at 34 separate points along the river. In a typical year, the system discharges 39 million tons of raw sewage and stormwater, a volume large enough to fill the Royal Albert Hall 450 times over. It is a controlled disaster designed to stop an even bigger one. London is forced to poison its own river just to keep its streets dry. Fixing this is a logistical nightmare. Excavating thousands of kilometers of urban roads to separate rainwater from sewage would paralyze the city's economy for decades. Instead, engineers went underneath the only open space they had left, the river. Buried 66 meters below ground is the Thames Tideway Tunnel, a 25-kilometer concrete bypass snaking beneath the curves of the water you see here. This depth created a massive structural challenge. When a storm hits, millions of gallons of water must be diverted from the surface sewers down into the deep tunnel. Dropping that much mass 60 meters straight down generates immense kinetic energy, enough force to scour concrete walls and eventually erode the tunnel from the inside out. To manage this energy, engineers use vortex generators. The inlet sends the incoming storm surge sideways against the curved outer wall. This geometry forces the water into a controlled spiral, using friction to dissipate kinetic energy. Reaching the bottom, the flow is smooth and safe. Managing this gravitational force allowed the project to successfully bridge the failing Victorian infrastructure with the new deep-level machine. Once the intake method was solved, the project faced the physical reality of carving out the tunnel itself. This required tunnel boring machines, underground factories the length of a football pitch that grind through the dense London clay. Inside the machine, robotic arms lock precast concrete segments into place, building a permanent waterproof ring. This happens 24 hours a day, entirely hidden from the surface. But excavation at this scale creates millions of tons of dirt. Moving it all by road would have required 700,000 truck journeys through narrow streets, causing total gridlock and massive air pollution. The solution was to use the river as a logistical highway. Spoil was moved up access shafts on conveyor belts and loaded directly onto barges, keeping the heavy industrial movement off the city's roads. This kept one of the largest infrastructure projects in history almost entirely detached from the daily lives of the millions of people living above it. Inside the finished 25-kilometer tunnel, the system operates with a distinct industrial logic. It moves water through the city without the need for massive mechanical pumps. The entire structure is built on a precise downward gradient, dropping 1 meter for every 790 meters it travels. Gravity pulls the weight of the storm surge east, moving it deeper and deeper as it leaves central London. The tunnel's sheer width allows it to act as a 1.6 million cubic meter holding tank, successfully absorbing the sudden, chaotic volume of a storm. The wastewater eventually reaches the Beckton Sewage Treatment Works, the largest plant of its kind in Europe. Here, the surge is finally pumped up for processing. Mechanical screens remove debris, organic sludge settles out in tanks, and oxygen is pumped into aeration lanes where bacteria consume the remaining microscopic waste. The tunnel isn't just a transit pipe, it's a massive shock absorber. It holds the chaos of a rainstorm until the surface treatment plant is ready to handle it. When you walk over Westminster Bridge on a rainy afternoon, the city feels normal. The traffic moves, the river looks calm, and the drains swallow the rain. That sense of ease is a manufactured illusion. Beneath your feet, millions of gallons of contaminated fluid are being quietly intercepted and spun down massive, high-speed concrete vortexes. It is a system of immense physical force, relying on gravity and 25 kilometers of concrete architecture to work in total silence. Modern urban life is made possible by this hidden machine, quietly keeping the metropolis from drowning in its own footprint.